So I explained Newton's three laws. Using the Newton's three laws, we could find the acceleration of an object. So this is the application of the Newton's three laws. Equilibrium state means is a body at rest or moving with constant velocity. Zero net force is from the Newton's first laws. So V equals 0 or V equals constant speed, then net force has to become 0 from the Newton's first law. So total amount of the force is 0. If you express in the component, x component and y component, z component have to be 0. So it is better to draw a figure with an object and the forces acting on it to apply Newton's three laws. So this is a free body diagrams. Shows the chosen body itself free of its surrounding, with vectors drawn to show the magnitude and directions of all forces applied to the bodies by the various other objects. So in this situation, we consider apples on a disk. Then we'd like to draw apples free from its surrounding. So this means the disk. Draw the apples, and then now we'd like to draw the two forces acting on the apples. Is gravities. F sub g is mg is gravity, and the normal force acting on the apples from a disk, F sub n. So this is one of a simple example of the free body diagrams. In the question of the physics, always you need to draw the free body diagrams. The example is a hanging object. Object is hanging with a rope on a ceiling. Then we'd like to draw the free body diagrams. So rope and the object is separated, and we draw all the forces acting on this object. For the object, gravitational force of the mg, capital M, is a mass of the object. And the Tm on M, this is a tension force acting on this object from this rope. And this is the action. Then we have to consider reactions. T capital M on M is a rope. So this is the action and reaction pairs. Then gravity acting on the rope. And the tension force ceiling on rope. This is a tension force. So then you could find that all the forces are drawn in these free body diagrams. You could easily confirm. Then you can express these hanging object doesn't move. So total force, net force, have to be 0. So for one object, two forces acting on this object. If you choose the upward direction is the positive directions, Tm on M minus mg equals 0. For the rope, this is the forces acting on the rope from ceiling minus mg. Mg is a gravitational force is directed downward. And the T sub capital M on rope. So tension force from an object to a rope is a directed downward direction. So you should put a negative sign. So net force is 0. So this is 0. So this is we applied Newton's first laws. Net force has to be 0 because the object doesn't move. Then actually for the rope, we have derived this equation. So most of the case, rope is a very light rope we consider compared with the mass of the object. So we substitute mass of the rope is 0. Then tension force C on M, these quantities, and M on M, capital M on M, this quantity, have to be equals. So tension force are the same at the both end of a rope when we consider a rope with a negligible mass. In the most of the physics questions, we ignore the mass of the rope. Otherwise, we need to take into account the mass of a rope. The next question is the object on the inclined planes. So in this case, the object doesn't move. So we can apply the Newton's first laws. So first of all, we need to draw the free body diagrams. So object is drawn away from the planes and also the rope. So three forces acting on this object: tension force, and the normal force, and the gravity. Gravitational force is acting downward directions, and then tension force is parallel to the slope, and the normal force is perpendicular to the slope. Then we'd like to write down the equation. And in the direction of the slope, we choose the x-axis, and the perpendicular directions with respect to the slope, we choose the y-axis. Then we have to decompose the gravitational force into the two vectors. This is the horizontal line, this is the slope, so this is going to be theta. Then you can find that this angle becomes theta. So magnitude of this is this is going to be mg, so mg cosine theta. This is mg sine theta. So for the x-axis, t is a positive direction, t minus mg sine theta, t minus mg sine theta. For the perpendicular direction in the y directions, n minus mg cosine theta, m minus mg cosine theta. So we decompose the gravitational force into the two directions. Then we have studied how to apply the Newton's first laws. Now second laws, use of the how to apply the Newton's second laws. Newton's second laws, we can study the dynamics of an object. A body object is not in an equilibrium state. Net force is not zero in this case. So we could write down the MA equal F. So in the component form, we have three equations. So first one is an object on an inclined planes. So first of all, we'd like to draw the free body diagrams. The object away from inclined planes. Then two forces acting on this object, gravity and the normal force. So if we consider the frictional force, we have to also draw the frictional force. But in this case, we consider the only really simple case. We ignore the friction. Then two forces acting, normal force and gravity. The x-axis is we choose in the direction of the slope. So if you draw this angle, this is theta. Then we'd like to decompose the gravity as a sum of these two directions. Then this is gonna be theta. So this magnitude is mg cosine theta. This is mg sine theta. Then we apply ma equal f. So mass times acceleration. Acceleration is directed toward the x-axis. So ma sub x is mg sine theta. This is the only force acting on these directions. ma sub y equal n minus mg cosine theta. In this direction, this object doesn't move. So a sub y equals 0. So equal to the 0. So in the direction of the y direction, we apply the Newton's first law. Net force has to be 0. The next case, the two objects attached with the strings. To solve the motion of these two objects, the red object has a mass of the capital M. Blue object has a mass of the lowercase of the m. Then, first of all, we'd like to draw the free body diagram. So in this situation, we need to draw the free body diagram for each object, for the blue ones and red ones. For the blue object, actually the three forces are acting: gravitational force, normal force, and tension force. For the red object, two forces are acting: gravity and the tension force. Then we'd like to write down the equations. For the blue ones, we apply second law. Mass times acceleration is equal to the t, because the tension force is a horizontal directions, and the a sub x, we choose a sub x is directed on the horizontal directions. So m times acceleration is a force. For the normal directions, perpendicular direction with respect to the floors, so 0 equal n minus mg. For the red object, acceleration of the blue object and the red object should be the same. So we choose a sub x. These two a sub x exactly the same. So mass is a capital M times acceleration equal to the gravitational force of the mg minus t is tension force. So by combining these two equations, you could find, if you sum up these two, mass times mass over a sub x equal mg, because the tension force is going to be cancelled out. So from this equation, you can find acceleration of the object. These two objects is given by the capital M over the lowercase of the m plus capital M times g. And the tension force, accelerated object. This object is pulling upward directions with the tension force of the t. Then we'd like to calculate the acceleration. So two forces acting on this object, tension force and gravity. We apply the equation of motion, ma equal f. M is the mass of the object. A sub y is acceleration, is directed upward. We consider the upward direction is a positive direction, so t has a positive direction. So t minus mg is a negative direction, minus mg. So this is the equation. So from this equation, you can find the tension force is expressed mass times acceleration plus g. So we could use this equation to find the tension force. Okay, this is the end of this session.